Hi, this is Adam Griffin with the first video for this week. So we are going to be doing problem number 2, and it goes like this. So we have a pendulum with a massless rigid rod attached to a sphere of radius r and mass m, as shown to the right, and the distance between the pivot and the center of mass is L, and we assume that the pendulum is on the surface of the Earth. So for part A, we use the parallel axis theorem to find the movement of inertia of the pendulum about the pivot, and the moment of inertia of a solid sphere is 2/5 times the mass times our radius squared. So the parallel axis theorem says that our inertia equals the inertia at the center of mass plus the mass of the entire thing times our distance squared, which would be L. So because this rod is massless, we don't need to worry about where the center of gravity is because it's all right here. So it's in the center of our sphere on the pendulum. So we get that the inertia of our object is the inertia of one of our objects plus the inertia of another object in our little system here. So that's the inertia of our sphere plus the inertia of our rod. So our inertia equals 2/5 times our mass times our radius squared, which we got up here, plus the inertia of a rod, which is this, which equals 0 because, again, it's massless, so this term is 0, plus, and then this is a different mass. This is the mass of the entire thing times our distance squared. So that comes out to 2/5 times our mass times our radius squared plus our mass times our length squared. So that is the inertia of this entire thing. So for part B, it's asking what is the torque on the pendulum if it is displaced from the vertical by an angle theta. So we have theta right here, and we know that torque is always equivalent to the radius times the force times sine of this angle right here, which is the degrees away from the direction that this thing is pointing. So in this case, it's the same as theta, and it is positive because this is clockwise from vertical. So we can write that again, where our term force times our sine of this angle is equivalent to our mass of the sphere times gravity times sine of this angle, because these two angles are the same. So we also know that our radius is equivalent to our length, so we get that the torque is equivalent to the length times the mass of our sphere times gravity times sine theta. And then finally for part C, we're finding the angular velocity for small displacements and whether or not it depends on m. So we know that frequency is equivalent to 1 divided by our period of oscillation, and our angular frequency is equivalent to 2 pi times our frequency, which is equivalent to 2 pi over t. And we have our equation for t, which is 2 pi times the square root of our length over g. And we can put those all together and we find that our angular frequency equals the square root of g over our length. So this obviously does not depend on m. And yeah, that's how you do this problem. Mostly it deals with inertia and torque. And yeah, that is the solution. So I hope it was easy to follow, and thank you.